Hi, hello, welcome back. Welcome back to CS 700, Computer Science of Continuous Data Algorithmic Foundations of Numerics. And we're talking about section 2 of the course, Real Computability. And within that section about part D, uncomputability that occurs with real functions. So item C was about computability of real functions, and item D is about uncomputability. And we've last time discussed and proven several examples of operations that involve computable real functions, but where these operations can leave the realm of computability. And these operations were actually pretty natural and common operations in numerics supported by common libraries like the NAG library. They include, for instance, automatic differentiation, right? That's a popular, huge topic in numerics. If you have implemented a function, let's say in your favorite programming language, real function, and you also want to be able to access the values of the derivative of this function. Is this possible? Well, the counterexample that we saw from Myhill demonstrates that even if the computed function is continuously differentiable, so its derivative is continuous and therefore satisfies the requirement of any computable function must necessarily be continuous. Nevertheless, this counterexample was constructed in such a way that it in general need not be computable. So let me start the slides so that you can see that. So here are the slides. Right, so yes, here we are. So this example of Myhill demonstrates that even if the function is computable and continuously differentiable, then in general still its derivative need not be computable. Provably, we've put in much effort to encode the halting problem, discrete infinite problem, into one carefully constructed and admittedly artificial instance uh, um, uh, continuously differentiable function, one single function, so not infinitely many as in the discrete case. The halting problem, any finite subset of the halting problem is of course decidable, but only the infinite part is undecidable. And we've carefully encoded the entire infinite halting problem into one single function, which was constructed such as to be computable and continuously differentiable, but its derivative is not computable. And as I kept emphasizing, this demonstrates fundamental limitations to what automatic differentiation can achieve rigorously. Certainly in many and maybe arguably even most practical cases, it works well. But since we're not engineers but scientists, that's not good enough for us. We want to be able to rigorously specify in which cases it works. And actually, in today's lecture, we're going to see such sufficient conditions when is they actually turns out to be sufficient and necessary conditions for a computable continuously differentiable function to have a computable derivative. So what is new in this lecture is that we get generally will complement the negative counterexamples from last lectures with positive examples. And that also extends to the next case, namely the wave equation. As you recall, we've established that the wave equation can map a computable initial condition to a rigorously provably uncomputable solution. Even the single value, the real number at a specific point in space and time, specifically at the origin in space, and that time step 1 is probably uncomputable for this, again, admittedly artificially constructed, but existing initial condition. On the other hand, what we learned today is that the wave equation is computable. It does map computable initial conditions to computable solution. However, we need to proceed to a different notion of computability, which is in agreement with the theory of partial differential equations, the solution theory, the existence and continuous dependence of solutions. That is called the partial differential equation problem must be well posed in the sense of Hadamard. And the third counterexample, which we discussed in last lecture, was the argmin and the root of function, or actually multi-valued function. We will talk about multi-functions in section E of chapter 2, but already now we've seen, we've constructed, or we've seen a construction of Ernst Becker of a computable function, which is therefore necessarily continuous, and actually of a computable infinitely often differentiable function, which classically attains its minimum, and by construction this minimum actually has the value 0, but it, by our careful, or Becker's careful construction, its minimum is not attained in any computable argument, and therefore also it has no computable root, although it has many roots. And actually the construction which we had to interrupt last time due to lack of time shows that the set of roots has a positive measure, so that it's a pretty large set in measure, theoretically speaking, but still none of these roots by construction is computable. And that is a topic of so-called singular coverings of computable reals, which we'll resume also today. And finally, the end and arguably most abstract part of this section D on uncomputability real function is about how compactness becomes crucial, a crucial generalization to finiteness from the discrete setting to the continuous setting of real computation, and more generally to computing on topological spaces, which we will discuss in chapter 3 actually of this course. And the general underlying intuition is that our sometimes so-called main theorem, any computable function must necessarily be continuous, has a generalization, namely that any computable function null must also necessarily be continuous. Remember that a functional is something that a higher type object that receives a function or functions as arguments and returns single numbers, let's say real numbers, as value. So this is of higher type functions receive real number arguments and return real number values. Function nulls receive real function, in our case continuous real functions, as arguments and return single real numbers as values. And we will later prove that any computable function is necessarily continuous. But in order to discuss that, that will only be possible in section F of the current chapter. To this end, we first have to discuss and introduce what it means to compute a functional, what it means to input a function, real function, as an argument, because so far we've only defined what it means to input a real number and to output a real number. So therefore this sentence is currently deliberately put into quotes and in italic, but this is maybe can help you understand or give a different perspective on all these counterexamples, because so let me proceed and recall this construction, or let me skip over the construction. We've discussed that extensively last time. So what I want to emphasize today is this new perspective of continuity as a necessary condition for functionals. Maybe you know from functional analysis that the differentiation operator is a discontinuous operator with respect to the supremum norm. So let me remind you of that. So here you see an example of a continuous function, continuously differentiable function. Actually, it's the sine function, right? It's a very good function, smooth function, infinitely often continuously differentiable. And now let's not consider, let's consider the derivative of the sine function. The derivative of the sine function is, of course, the cosine function, which is basically the same function just shifted. So it has same nice properties. And in particular, the derivative of this function is bounded between plus and minus 1, right? But now we're going to do the following. We're going to scale that function. And we're going to scale that in both directions, in x direction and in y direction. Now, when we scale that function in y direction, that means that the norm of this function, the supremum norm, the maximum norm, also decreases, becomes smaller, right? So when we make that amplitude smaller, then also the supremum norm of that function becomes smaller. At the same time, when we scale the function smaller in x direction, then it basically intuitively it becomes steeper, right? If we kind of squeeze it in like that, then that means that the slope increases and therefore the derivative increases, becomes larger, okay? And when we do both at the same time, as you see here, so we have shrunk the function in both directions. And if we continue that process, that means that the function converges in supremum norm to the zero function, right? If we continue scaling in y direction, so that the function becomes flatter and flatter, the amplitude reduces, then this function converges to the zero function. At the same time, since we've been scaling x direction as well, that means that the derivative of this function, of this family of functions, grows. And if we continue that process further, then that means that the derivative of this function is unbounded. And in particular, the derivative of this family of functions, let me repeat the scaling, the derivative of this family of functions does not convert to the derivative of the zero function. So this is a reminder of you of a family of, or sequence of functions, smooth functions, which converge to the zero function, but their derivative does not converge to the derivative of the zero function. And that is a reminder that the differentiation operator is not a continuous operator, at least not with respect to the supremum norm. And this is exactly what underlies the Myhill's counterexample with all these heads. As you recall, we have deliberately made the heads thinner and thinner, and thus increased their slope, and that means increase the derivative while keeping the scaling, or while simultaneously scaling the y direction, so that the function still remains continuous even at zero. So that's an intuitive idea. Yeah, basically, since the differentiation operator is discontinuous, it cannot be computable according to the yet to be proven extension of our main theorem. And Myhill's merit is that he has constructed or used that property to explicitly encode the halting problem into such a counterexample. So that's the gist. And the purpose of this new slide is actually to demonstrate a counterpart to that, namely sufficient and actually it turns out also necessary conditions for the derivative of the computable continuously differentiable function to be again computable. And we have the following theorem. Suppose we have a continuously differentiable function on the unit interval, let's say, a real function which is computable. And the statement says its derivative is again computable if and only if that derivative has a computable modulus of continuity. And as you recall, modulus of continuity is a function from natural numbers to natural numbers that quantitatively captures uniform continuity. And one of the three characterizations of computable functions was that any computable function must have a computable modulus of continuity, right? That was one of the part of the condition of one of the three notions. So indeed, this is a necessary condition for the derivative to be again computable, requires that the derivative has a computable modulus of continuity. It certainly has a modulus of continuity since the derivative is continuous, right? Derivative of the C1 function is continuous on a compact domain and therefore uniformly continuous. And uniformly continuous means having a modulus. But the requirement here is that it must have a computable modulus. And the interesting part of the theorem is that the converse also holds. If the original function is such that its derivative not only has a modulus of continuity, is uniformly continuous, but if it has a computable modulus of continuity, then already the derivative is computable. And that's maybe quite surprising. So let us have a look at this interesting direction of this equivalence if and only if. But first, let's consider another interesting corollary for that. Maybe let's consider a C infinity function, a smooth function, a function which is infinitely often continuously differentiable, like this function here, right? Remember we talked about, for instance, the mollifier, right? That was an example of a smooth function with compact support. And the statement or the corollary of this theorem, which we'll prove in a minute, the corollary says if such a smooth function is computable on a compact interval, then actually every single of its derivatives is again computable. We don't need any additional hypothesis about modulus of continuity of the derivatives. But there's a subtle point involved here, namely each single derivative. It doesn't say that there's an algorithm that computes all the derivatives, but each single derivative may in general require a different algorithm. This is, remember how we proved that any real number that has a computable, that can be computed by means of dyadic rational approximations, then such a real number also has a computable binary or decidable binary expansion. In this proof, we actually constructed several algorithms. One algorithm is the real number under consideration is not a dyadic rational, and then whenever the real function number under consideration is a dyadic rational, then we would hard code that into the algorithm and therefore have actually infinitely many algorithms, one for each possible dyadic rational value. And the same happens here. Here we're going to, we can conclude that every single derivative has an algorithm that computes it, but not necessarily one single algorithm to cover all possible derivatives. And the reason for that becomes apparent when we now look at the proof of the corollary first, namely consider the case derivative. The case derivative is continuous, right? Because the underlying function is smooth, right? So that means the case derivative exists and is continuous. But in fact, the case derivative is Lipschitz continuous, right? Why is the case derivative Lipschitz continuous? Well, because the k plus first derivative is continuous and therefore bounded, right? The k plus first derivative is also continuous. It's c infinity. And a continuous function on a bounded compact interval is bounded. So the k plus first derivative is bounded by some natural number, let's say by some natural number m. And we can hard code that natural number, right? It's a finite object, finitely many bits. We can hard code that into an algorithm. And then that algorithm can use that constant, right? Remember, a Lipschitz continuous means that it has a modulus of continuity of the form n plus a constant. And this constant is hard-coded now in our algorithm. So in particular, the case derivative has a computable modulus of continuity, namely the modulus n plus the integer constant, which was hard-coded, right? And therefore, according to the theorem, which we're going to prove in a minute, that means that the case derivative indeed has a computable modulus of continuity, namely modulus n plus a constant. But of course, the question is, what is the value of that constant, right? And the argument, the proof we just gave, only says that there exists a constant, which is going to be hard-coded in the algorithm, but it does not say how we, or even worse, how an algorithm could possibly find that integer constant. And it also demonstrates indeed that when we consider another derivative, then we will going to need another integer constant. So let's say we consider the else derivative. That is again Lipschitz continuous, namely with a constant depending on the bound of the L plus first derivative, which is continuous and therefore bounded. But again, for L, we need a possibly different constant in our modulus of continuity, n plus a constant. And we only know and can prove that such a constant exists. So for every different k or L here, the kth and Lth derivative will in general need a different integer constant to be hard-coded, and therefore we're going to have different algorithms for each of these derivatives. I mean, for any finite number of derivatives, of course, we can hard-code the finitely many of these constants, right? But there's not, in general, actually, there's not one single algorithm that computes all derivatives. Okay, and that follows from the theorem, right? So that is a demonstration of the power of this theorem, which characterizes precisely in which cases the derivative of a computable and continuously differentiable function is again computable. And now, finally, as I've announced often enough, we can proceed to see the proof of that theorem. And as I said, one direction is obvious. We already know that computable modulus of continuity is necessary for computability. So let's now look at the converse. And we're going to describe an algorithm which evaluates the derivative up to any error 2 to the minus n at any given argument x inside the domain, inside the unit interval. So we're given a real number, which is a real argument, and a precision parameter, and the goal is to output an approximation to the derivative f prime of x up to this error 2 to the minus n. And here's the algorithm, output this expression. Well, to be fair, this is not a rational approximation, this is not a dyadic approximation, but as you recall, if we can produce approximation in any rational number, dyadic rational number, or whatever, up to error 2 to the minus n minus 1, then it's easy to truncate and round that to the next dyadic rational, and that is sufficient. So what is this expression? This expression is a difference quotient, right? So this is a f of x plus delta minus f of x divided by delta. And as you know from basic calculus, when delta tends to 0, this quotient tends to the derivative f prime of x. But you also remember that having ordinary limits, delta to 0, can in general leave the realm of computability. So the question is, why can we compute the limit in this case? And actually, more precisely, why is this finite, right? So this is not a limit. Namely, we're going to choose a very specific value for delta. Namely, delta is 2 to the minus mu of n. And we can do that because that's where the hypothesis enters, right? Our hypothesis says that f prime has a computable modulus of continuity mu. And this is exactly this mu that we use here to define, to choose delta. And the claim is that when we choose this value for delta, then that's good enough to approximate the actual limit delta to 0 up to error 2 to the minus n. And why is that the case? To this end, let us recall the mean value theorem, not the intermediate value theorem, but the mean value theorem. The mean value theorem says if the function is continuously differentiable, that's crucial here, not just differentiable, but continuously differentiable, then that quotient is equal to the derivative, not necessarily at x, but at some argument y in the interval from x to x plus delta. To recall that, that's a mean value theorem, right? There exists some argument in this range from x to x plus delta, such that this finite difference quotient is actually equal to the derivative to the limit at a different point y, okay? And that's what we're going to use. And again, recall that here we don't need any constructive version of the mean value theorem. We only need to know that such a y exists. And then we use the estimate, namely the estimate that mu is a modulus of continuity of the derivative, because namely now by hypothesis, the value of the derivative at x, that's where we want to know the value, differs from the value of the derivative at this unknown argument y, which however is in this interval, by at most 2 to the minus n. That's the definition of modulus of continuity. Since x and y have distance at most 2 to the minus mu of n, right? Therefore, by the definition of modulus of continuity means that the values of the derivative differ by at most 2 to the minus n, which was exactly what we claimed and were supposed to do, namely approximate the value of the derivative at x. Okay, so to summarize here, Myhill demonstrates that in general, computable continuously differentiable functions may have uncomputable derivative, but here we have a full characterization in which cases actually the derivative is again computable. Namely, necessary condition is that it has a computable modulus of continuity, and actually that's also a sufficient condition. And as a consequence of that characterization, every infinitely often continuously differentiable function which is computable has every single derivative computable, but not all of them necessarily, not necessarily all of them by one joint algorithm, because every algorithm that computes a derivative needs or has hard-coded some bound on the next higher derivatives value. Okay, so it was about positive and negative examples of derivative. And then we talked about the wave equation, where the proof was involved Myhill's counterexample. So here you saw the wave equation, partial differential equation. Partial differential equations are actually a pretty complex, complicated object of study in pure mathematics, namely the theory when a partial differential equation actually has a solution is a very involved one. For instance, one of the Millennium Prize problems about the Navier-Stokes equation asks or conjectures sufficient conditions for the Navier-Stokes partial differential equation to have, in a sense, good solutions solutions which don't blow up. Yeah, just as a little anecdote, so Navier-Stokes equation has been devised by mathematicians as in order to mathematically describe the flow of viscous medium like water, right? Not a pure, not an ideal liquid, but a viscous one, a little bit like honey, right? And that we cannot prove this equation to always have a solution which is free of singularities. That's quite embarrassing, because for the practitioner's point of view, for engineer, that's pretty obvious. You just turn on the water in your flow system, and then of course nothing nothing blows up, right? But proving that rigorously mathematically, that has been an open problem for many decades. Right, so the solution, mathematical solution theory of partial differential equations is very involved, and we've studied the computability here. Actually, people have studied that before, like Forel and Richards, and they've come up with this counterexample where, based on Kirchhoff's formula, which is a well-known formula known in classical theory of partial differential equations, to yield a solution, the unique solution of the wave equation. Actually, the proof proceeds differently. Suppose that U is a solution of the wave equation, then U must necessarily be of this form. And I'd also like to emphasize that there's some subtleties involved here. For instance, there's a division by t, so that only makes sense for t positive, right? There's a differentiation by t, and this is a term that is added for the that's the initial condition. That's the initial condition for the first derivative, which we also need to specify to make the problem uniquely defined, right? So here are two temporal derivatives, so we need to specify the first zeros in first derivative as initial conditions. And using Myhell's counterexample of a function from one-dimensional function, and extend that radially symmetrically, right? So that means the function value depends only on the length of the three-dimensional argument. So this is the three-dimensional wave equation we're considering here. So our initial equation depends only on the distance of the argument to the origin, not on the direction. It's a rotational symmetric initial condition, and therefore also the solution, of course, will be rotationally invariant. It depends only on the radius of the radius of the spatial argument. And then in this case, Kirchhoff's formula simplifies drastically to this expression, which already demonstrates that the solution here kind of consummates one derivative of the initial condition, right? So when we had H as initial condition, then H enters into the solution's value at the spatial origin 0 over time, right? But also the first derivative of the initial condition enters. And now, as you recall, Myhell's example was deliberately constructed so that this first derivative is uncomputable, and specifically uncomputable at argument t equals 1. So this is the reason why this solution at time t will be necessarily uncomputable. But when this counterexample was presented to mathematicians, they immediately pointed out, well, of course, why? Because the wave equation is well known to lose in general 1 degree of smoothness, of regularity of the initial condition as soon as the time proceeds from 0 initial condition to positive 0. And that's what we see here in this explicit solution formula. So let me state that a well-known mathematical fact that the wave equation loses regularity, loses 1 degree of derivative from the initial condition as soon as the time t proceeds from 0 to positive. And that applies also to higher derivatives. Let's say that the initial condition is not just computable and continuous, therefore, but let's say that the initial condition is k times continuously differentiable. Then mathematics says that the solution of the wave equation will in general only be k minus 1 times continuously differentiable. So one loss of 1 degree of differentiability, that's a loss of regularity that is well known in the theory of partial differential equations for the wave equation. Other equations, like for example, the heat equation, have an opposite effect. They gain regularity as time increases. But that's a different topic. That's so let's proceed to the kind of resolution. Namely, intuitively, we would expect any physical process to be computable, right? That's a Church-Turing hypothesis. And indeed, this is kind of the case. Before that, I should also give another counterexample. Namely, here we have a lossless regularity in time, but there's also well-known counterexamples that demonstrate the loss of regularity in space. And if we consider an initial condition for simplicity in spherical coordinates, remember, for simplicity, we focus here in the case where the initial condition and the solution depends only on the radius. More generally, we're going to now consider the case where it depends on the radius and on one of the two angles that define spherical coordinates. And we're going to consider this initial condition. Let's have a look at this initial condition. Here's the dependence on the radius. So this is in case that the radius is between 1 and 2. So this expression is a quadratic expression which vanishes when radius is 1 and vanishes when radius is 2. And between 1 and 2, it is positive. Right? And how about this? This is the angular condition, namely again, quadratic condition which vanishes at two angles, pi over 6 and pi over 4. And between pi over 6 and pi over 4, it is strictly positive. And outside of this region in space, whenever the radius is outside 1 and 2, whenever the angle is outside pi over 6, pi over 4, then we define our initial condition to be 0 and observe that this is a continuous initial condition, namely outside of this region or at the boundary of this region. For instance, at the boundary when r is equal to 1 or r equal to 2, this part vanishes. And whenever the angle is pi over 6 or pi over 4, then this part vanishes. So this is a way of continuously extending the first case to the whole space continuously. And then it's an exercise in calculus that I'd like to leave to you to evaluate the Kirchhoff's formula in this case and verify that now the solution will exhibit a discontinuity in space. Here was a discontinuity in time at the origin, and here there will be a discontinuity in space from the origin to outside of the origin at time, let's say t equals 1. So here you see the solution in the origin. These are the spatial coordinates at time 1 is non-zero, whereas a little bit down the z-axis, right? So the last coordinate is the z-axis at time t is non-zero, so there's a discontinuity here. And so, as I said, right, mathematically this has been well known that the solution will lose 1 degree in regularity. So if we start only with the continuous initial condition, then in general the solution will be discontinuous. And the Puel and Richards example is a case where the solution is still continuous, but involves carefully constructed to involve a coding of the halting problem. And this problem, kind of or surprising statement, was resolved by Klaus Weyrauch and Ning Zhong in 2002, when they rigorously proved what, again, mathematicians had kind of known all the time, namely, one should consider initial condition and solution not within the space of continuous function or continuously differentiable function with respect to the supremum norm, but one should consider them as in the space, in the LP space, and with respect to weak derivatives, that is, as elements of Sobolev spaces. That's the solution theory of partial differential equations. In this setting, the wave equation is well behaved. There's no loss of there's a continuous dependence on the solution on the initial conditions, so the problem then becomes well posed, and Weyrauch and Zhong has proved that in this sense and setting, actually the solution is computable, not a uniform approximation of the value, but approximation in the Sobolev norm. And the Sobolev space of function has this subtle property that you cannot evaluate a Sobolev or more generally an LP function at an argument. So it doesn't make sense to ask for the solution's value in the origin, because integrable function is only defined at up to changes at a subset of measure 0. And if that origin belongs to that measure of 0, we can change the value at the origin arbitrarily without affecting the metric of that function. So even writing down such an expression makes no sense in Sobolev space. It only makes sense in space of continuous functions with respect to the supremum norm. And so in order to rigorously prove that statement, Weyrauch and Zhong have and had to devise a rigorous notion of computability for spaces of integrable functions and for spaces of weakly differentiable integrable functions, that is for Sobolev space. And that's what I actually did in order to prove that. Okay, so right, this is the summary of the computability of the wave equation, whereas the previous slide was about uncomputability of the wave equation. And finally, we were to talk about uncomputability of the argmin function and of the root of function. But before that, let us talk positively about computability of the root of functions. So you're already maybe embracing for the negative example, but first let's see sufficient conditions for when the root of a function is computable. And so to this end, we're going to look at the intermediate, not the mean, but the intermediate value theorem, which says, gives sufficient conditions for a continuous function to have a root, namely if the function is on the unit interval and it's negative on one end and positive on the other end, then by the intermediate value theorem, it must vanish somewhere in between. It must have a root somewhere between 0 and 1. F necessarily has a root, maybe several roots, right? It could have several roots, but it has at least one root, at least one argument x, where the function value vanishes. Now let's follow our paradigm here, that any computable functional is continuous, and consider that functional, the root finding functional, on the space of not arbitrarily continuous function, but restrict to the space of functions where continuous functions which satisfy this sign changing property. And here you see such an example of such a function. It's a continuous function. It's negative at argument 0. It's positive here at argument 1. And so the intermediate value theorem, it says it has at least one root. And indeed it has. Here's a root, right? And let's now perform a stability analysis or sensitivity analysis. What happens if we perturb that function within the space of continuous function? If we slightly modify the function, slightly meaning with respect to the supremum norm, right? Space of continuous functions routinely equipped with a supremum norm. Now what happens, what you see here is that the root jumps, right? So small perturbation of the function, very small, like here this value, can be made arbitrarily small, can result in a huge jump of the root, of the unique root, right? So you see that the root is now unique again, but there's a transition. At some point, this family of functions has infinitely many roots, namely all of these. This is the constant section, right? And this is an important observation. So the first observation says that the root finding functional is discontinuous. Therefore, we expect it actually to be not computable. On the other hand, if we omit the case where the function under consideration has many roots, if we exclude that, then it turns out that the root finding functional is actually computable. But we're not talking about functionals here yet. Functionals will be discussed in in section F of chapter 2. So instead here we fix a computable function. For the computable intermediate value theorem, suppose we have a function like this, which is computable and satisfies this sign changing condition, and the statement says this f has some computable root. Okay, in general it will have many roots, but here the good news is there will always be a computable root. Okay, and now let's prove this statement, and the statement again will involve different cases, and there will not be an algorithm to decide which of the cases applies, but we prove that for every fixed such function there exists an algorithm. That's the same kind of argument as we had previously on the previous slide about computing any derivative of a smooth, computable smooth function on a unit interval, or the algorithms we constructed for deciding the binary expansion of any fixed dyadic rational as distinguished from the deciding the binary expansion from an other real number which is not a dyadic rational. So the same will exhibit here in our construction of an algorithm that computes the root. And the algorithm we employ here is going to be the classical numerical bisection. And for those of you who are already suspicious that we may use trisection, this is true when we talk about part F of section 2, computing functionals. But here we have a fixed function. We don't talk about how the function f is input. The function f is fixed. There exists an algorithm that computes it, and we construct an algorithm that computes a root for this fixed function, no input of a function. Okay, so we know from the classical non-constructive intermediate value theorem that this function f has at least one root in the interval from a to b, where a and b will be endpoints, enclosures of the real root. And during the course of the algorithm, these endpoints will become will get closer to each other, and thus get better and better approximation to a root in this interval. So initially A is 0 and B is 1. That's kind of our loop invariance. And here's the loop of the algorithm that says we evaluate the function at the midpoint. A plus B divided by 2 is the average, the midpoint. If that value is negative, then we're going to proceed to the right subinterval. We're going to increase the left bound to the midpoint and continue this iteration. If the sign of the function at the midpoint is positive, then we're going to continue and recurse to the left subinterval. We're going to decrease the right bound and continue. But yes, of course, there's a third case, right? Namely, if the value of the function at this midpoint is actually equal to 0, well, then we're going to return that midpoint, because then we have found a root, right? The midpoint is the root. Okay, and if you have paid attention, then you should complain, right? Namely, the test whether this value is 0 is, of course, not computable, right? We've discussed that length. Test for equality of real numbers. This is a real number. Test whether it's equal to 0. It's undecidable. But now here comes the subtle point of this algorithm. Actually, this is not just one algorithm. This is infinitely many algorithms. Namely, we're going to consider two cases. The first case is where the function f under consideration has a root which is a dyadic rational. If the function f under consideration has a dyadic rational as among its roots, then definitely has a computable root, right? Namely, every dyadic rational is computable. That's what we discussed when we talked about computability of single real numbers. So we may, without Loffort's generality, suppose that the function f under consideration does not have any dyadic rational as a root. And in this case, the third case will never occur, right? But this is a distinction that we as mathematicians make when we construct the algorithm. We consider two cases. If the function f under consideration has a dyadic rational root, then we use an explicit tailored algorithm that just outputs that root and completely ignores the function under consideration. Whereas if the function under consideration does not have any dyadic rational among its roots, it has roots, then we run this algorithm by section and can now eliminate the third condition. So we can safely run the algorithm using only the first two cases, and that, as you may recall, inequality is semi-decidable, so we will always be in one of the two cases, and eventually an algorithm can detect which of the two cases apply and therefore perform a regular computation interval bisection, producing smaller and smaller enclosing intervals to some root. Okay, right. There's a question in the chat. Thank you. Yes. Yes, Hono, exactly. It's a very good observation and point that I'm happy to pick up on. Yes, saying that it has a computable root and finding a root is a very different statement. The latter is a much stronger statement, and for the latter to be true, we need stronger hypothesis on the function under consideration. Here we only prove the first statement, which is weaker and deals with less hypothesis. This is like, I keep giving this example. It is decidable whether God exists. Then we to make two algorithms, one that says yes and one that says no, and one of them is correct. We don't know which one, but it is decidable. That's kind of a useless proof, and therefore maybe a useless statement. Similarly, we could say that this statement, the computable intermediate value theorem in the way we stated here in this slide, is not very helpful for practice, and I would agree to that. And later in section F of the current chapter, there we're going to consider the uniform problem given a function which is promised to have a root, find that or find a root. And that turns out to be much more difficult and delicate question. Thank you, Hyunwoo, and thanks for giving the opportunity to answer that. Okay, so yes, that concludes the kind of positive part of computable root finding. And right, so the nth iteration of that loop then gives error bounds up to error 2 to the minus n to a root. And maybe the important thing to distinguish here is computing approximations to a root or an approximate root. An approximate root means there exists some root in the vicinity of the approximation we give. But when we give better approximation, there might be a different root. Whereas here for computing a root, the better and better approximations must refer to the same root when we increase the precision. Okay, and now to recall the negative part that we'd already talked about last time was this construction, which we didn't quite finish. So let's conclude and continue that part. So we started with this computable piecewise linear head function, which had the property that it is positive on the open interval with center Cm and radius Rm. And when we have not just one such value Cm and Rm, but an entire sequence, computable sequence, then we can convert that into a function which vanishes precisely outside of the union of these open intervals. And I have called this a computable Eurison theorem, because Urison's lemma says that every closed set in an appropriate space is the set of zeros of a continuous real valued function. And this is exactly what we have here, right? So the set of zeros of a continuous function, a computable function, computable Eurison lemma, is equal to this closed set. Namely, take a compact unit interval and remove all this union of open set that results in a closed set. And there was a strengthening of that construction, and we can make the function not just computable and therefore continuous, but we can actually make the function smooth, C infinity, by replacing all these piecewise linear and continuous head functions with these also computable modifiers shifted and scaled appropriately. Right. Good. And based on that construction, now the construction had the hypothesis that there exist such sequences, and now we're going to use very specific such sequences, namely sequences, or rather intervals, open intervals, that cover all computable real numbers. So the statement is, there exist computable sequences of centers and radii such that the union of these countably many open intervals contains all computable reals in 0, 1. Well, that's a trivial statement, right? You can just consider, for instance, the single open interval from -1 to +2, right? That's one. We don't even need infinitely many such intervals. We just need one to cover all computable reals in the unit interval, to cover the entire unit interval. But the point is, we want to be able to cover only the computable reals. Now that's impossible again, right? Because the computable real numbers include all rational numbers, and therefore they are dense. So we cannot have open intervals cover all computable real numbers without also covering some non-computable real numbers. On the other hand, there are only countably many computable real numbers, same cardinality as rational numbers, but of course, many more than in addition. And for such case, in classical calculus, probably you have seen such a construction. Any countable subset of real numbers has the back measure 0, right? It is a zero set. Any countable set of real numbers is a zero set. What does that mean in measure theory? It means we can cover this countable set with open intervals of arbitrarily measure, right? So the measure of an open interval is just its length, right? And if we have countably many open intervals, then its measure is at most the sum of the lengths. And since we have countably many points for an arbitrary countable subset of real numbers, we can actually make the intervals around, choose intervals or take intervals around every single point in that countable set of radius that decreases exponentially. Then the total measure of this open set, the union of these countable open intervals, is at most a geometric sum and therefore finite. And by making the interval length decrease like 2 to minus n, therefore the total length or the total measure of this open set is at most the geometric series 2 to the minus m, that is 1 or 2. But by making the intervals even smaller, like 3 to the minus m, 4 to the minus m, 1700 to the minus m, in this way we can actually make the measure of the open set that covers the countable set arbitrarily small. And arbitrarily small, that's the very definition of having Lebesgue measure 0, right? Lebesgue measure is the infimum over all such coverings by open intervals. Now that's a classical exercise in calculus that any countable set can be covered by open intervals of arbitrarily small measure. But here comes the additional subtlety. Here we want to cover again a countable set, the set of all computable reals, which therefore has Lebesgue measure 0, can be covered by open intervals of arbitrarily small measure. But we want these intervals also to have computable centers and radii, right? And that's an additional challenge compared to the classical calculus exercise. And this is indeed what we can achieve. There exists computable such sequence of centers and radii, such that on the one hand, these intervals cover all computable reals, like in the classical case, and have, well, not arbitrarily small, well, indeed one can have arbitrarily small measure, but here we are suffice with measure less than 1/2, although the entire interval, including all non-computable real numbers, has of course measure +1, right? But the point is here, this must be computable sequences. And this is a pretty sophisticated construction. So please buckle up for what we're going to do in order to prove that. But first, the corollary by combining the two lemmas, the computable Eurison lemma, and this it's called singular covering lemma, computable singular covering lemma, or computable measure 0, Lebesgue measure 0 lemma, is the statement that I've already announced, Specker's statement. There exists a computable function and therefore continuous function from the unit interval to the unit interval, even a smooth such function that has many roots, that attains at minimum 0 in many points, actually in a set of points which has measure at least 1/2. The set of roots is very large, right? But avoids all computable real numbers. And that's obviously the consequence of combining these two lemmas, right? First, there exists computable such sequences that cover all computable reals and has small measure. And then second lemma says we can convert that into a function with the required property. And since this has measure less or equal than /2, the remaining set has measure greater or equal, or yeah, actually strictly greater than /2, 1/2. And this is the statement that says, in general, root finding and in general, argmin of a computable function is uncomputable, and smoothness hypothesis do not help, right? Even this hypothesis that the function is infinitely often continuously differentiable, still it's an uncomputable problem in general. And the difference is, as I said, approximating a root, which is the goal or the specification of the root of function or the argument function, approximating a root versus an approximate root. So for every finite precision we can have an algorithm that for any finite precision outputs approximation to some root, but when we increase the precision, that algorithm could return an approximation to a different root. And so the sequence of approximations are not guaranteed to converge to one single number, although every single finite approximation is sufficiently close to some root. Okay, that's a subtle point that is easy to confuse. Okay, what remains for us to do is to prove that singular covering lemma, right? And yeah, I guess that's all we can aim for in today's lecture. Amy, so here's for your convenience a reminder of what it means to compute a real number, namely to output numerators, integer numerators to diagonal approximations. And here we've used the Cauchy property, right? So without specifying which a real number is to be computed, some real number to compute some real number means to compute such a Cauchy sequence that satisfies this error bound, then it's easy to see that such a sequence indeed converges by the Cauchy property and converges to some real number which it approximates up to error 2 to the minus n. And we now use that property, that reformulation of what it means to compute a real number, to diagonalize. The same thing we did when we proved the halting problem undecidable. Namely, we're going to construct a sequence of such centers in radio that cover all possible computable real numbers. And to this end, we enumerate all possible computable real numbers, or more precisely, we enumerate all algorithms that compute real numbers. And the difficulty here is that, of course, we cannot decide whether a given algorithm actually computes a real number or not. By simulating the algorithm, we can check whether the algorithm outputs finitely many approximations that satisfy this condition, but we can never be sure that the algorithm outputs an infinite sequence where every element of that infinite sequence satisfies this condition. That's, of course, impossible. That's right. So, but instead what we're going to do, we're going to take an optimistic approach and just enumerate all possible algorithms and assume that the algorithm we're currently considering does output approximations to some real number. And if during the simulation of that algorithm it turns out to be not the case, then we're going to discard that algorithm. So that in the end, in the diagonalization process, indeed only those algorithms remain and persist that compute real numbers and therefore computable real numbers. So here's the our diagonalization algorithm. We fix program P, an algorithm, in some enumeration, and we're simulating it until it outputs that many numerators of diagonal approximations. The number, the index of that algorithm, right? Remember, every algorithm is encoded as some natural number, and for a reason that will become clear in a few minutes, we add 4. So we simulate the algorithm until it outputs that. If the algorithm never outputs that many numbers, then that's a different issue that I will address at the end of discussing this slide. But let's for now suppose that our simulation succeeds. Then that means that the algorithm has produced approximations to some real number and possibly continuous computing a real number. Right, so we verify that approximation that produces satisfy this necessary condition, but only we verify the finite initial part of that infinite sequence of approximations. And then in this case, we output our algorithm computing these sequences, outputs the following sequence element that corresponds to the number of the program we're currently simulating. We take the index of the program +4 and use it as numerator to diagonal approximation with same denominator. And the radius we consider is basically twice the radius of that approximation, right? So here it's +4 and here it's +3. That means the radius is twice as high, twice as large. That will become apparent in a minute. It's basically because by triangle inequality, it means that whatever real number this algorithm continues to compute, if it computes a real number, that real number will be contained in the open interval with that center and that radius. Because as it keeps continuing to compute the real number, then the approximation will be better and better, and therefore at most twice off from that center, and that's the factor 2 that we take into account here. So to summarize the first part of this proof, if the algorithm P does compute a real number, then that real number is contained in that open interval with this center and this radius. If it does not compute a real number, if it never gets as far as to output that, or if it violates some of this condition, then we just discard the algorithm. But if it does so far, then we output this interval, and therefore this interval covers the real number that possibly is computed by that algorithm. And by doing that for every possible algorithm, whether or not it computes a real number or not, we make sure that these intervals indeed cover all possible real numbers. So that's the first property. These intervals we've just constructed an algorithm for indeed contain all computable real numbers. And the next property is about the measure. But this is or we choose this interval size, namely the measure is, well, the measure of one single interval is twice the length of the interval, which is twice this radius, right? And since this radius converges, or this radii, as we range over all possible programs, these radii are just geometric sum and therefore bounded by 1/2. And that's the second claim. So to summarize, this is just a kind of variation of the classical calculus statement that every finite set has Lebesgue measure 0, can be covered by open intervals of arbitrarily small total measure. And here we refine that construction to be a computable centers and radii of open intervals that cover all computable, countably many computable reals, and have arbitrarily small, in this case, measure 1/2. And of course, we can replace 1/2 here by choosing different values here. Okay, so that concludes the singular covering lemma, which we've used in the proof of, in the construction of Ernst Becker of a smooth computable function, which has many roots, which attains its minimum in many arguments, actually in arguments of measure at least 1/2, but none of them is computable. Okay, and yeah, it seems time is already up. So what we're going to discuss next week is compactness in bare space and how that affects quantitative and qualitative continuity. Namely, I still owe you the proof that not only every computable function must be continuous, but every computable function has a computable modulus of continuity. And that's what we're going to prove next week by recalling notions and properties of compact Baire space and then translating those to the real setting.